Welcome back, ladies and gentlemen. Let's continue on. We're talking about, so we spent some time kind of in chapter 2 of this text talking about I've readjusted my camera angle, so it's going to take me a little while here. So this is going to be lecture 5 and 6. This is page 1. This is going to be focusing on chapter 3 in the Chengel and Bowles text. Talking about properties of pure substances. Basically using property tables. Now, why is that important? Well, as I mentioned, we previously talked about the first law. So we introduced the first law, and if we look at the first law for closed systems. Right, so in the last couple of videos we talked about the first law. We talked about efficiency. We introduced the concept of efficiency. We talk about that in chapter 2 of the Chengel and Bowles text. First law for closed systems. And again, the first law, it's this big, long, ugly equation, but which you can memorize if you like, or you can just think about it as in minus out equals change. And if you think about it as in minus out equals change, then you think about, well, okay, what are the ways energy can come into the system? Well, if it's a closed system, it's going to be work and heat. And that's it. If it's a control volume, then that means mass can also cross the system boundary, and we'll need to keep track of the energy of that mass. But if it's just a closed system, it's heat and work, and those same quantities can go out. So add the work in, add the heat in, minus the heat out, minus the work out. Interchange these first 4 terms in any direction you like, as long as you keep track of the sign. That's equal to the change in the energy of our system. Well, what types of energy can the system have? Well, if it's a closed system, it can have its own internal energy. It can have its own kinetic energy. And it can have its own potential energy. Now, these are quantities we would need to be able to measure: the speed of the system and the potential energy, the elevation of the system. Right? So these are things we could measure. This is not necessarily something we can measure very easily, the internal energy. These are quantities we talked in chapter 2 about various ways to find work. Heat is, for us at this point, is something we're going to need to be able to find, or we're using the first law to find this quantity, or has to be given to us, or maybe they've told us it's negligible, that like we need some, unless the heat is what we're looking for, because again, this is one equation, so there's only one unknown I can solve. So unless heat is what I'm looking for, I need to have some other way of knowing what that quantity is. We have some tools for work, we have some tools for these guys. What do we do with these U values? Well, that's the whole focus of chapter 3, where we talk about properties of pure substances. Again, that's for us, that's chapter 3 in our text. And that's going to be our whole focus here, right? So how do we find U, right? How do we find a U value? Well, there's not a big fancy equation that we just plug variables in. I mean, it actually probably is. It's going to be a computer model. It's not something that we work with. We don't have this equation to find a U value. What we have is we've got property tables. Or, and actually for an ideal gas, there is actually a pretty simple formula that we'll use to find delta U. We'll talk about that as we get a little closer. So the truth of the matter is, it depends on what is my substance, and that's going to tell me what I do with U, and how do I find U. So let's start down that path. So to get there, we need to talk about what is a pure substance. Right? How do we figure out, how do we find the U value? Well, so again, I've got my notes here. This anytime you see a direct quote there without a source, that's a direct quote from your text, the Chengel and Bowles text. They define a pure substance as any substance that has a fixed chemical composition throughout. Okay. It can be a mixture of several elements. It doesn't have to be a pure element. It doesn't have to be pure oxygen or pure nitrogen. Water can be a pure substance. It doesn't even have to be an elemental compound of any kind. Like water's fine, but it doesn't have to be water. It could also be something like air, the air that we breathe, AIR. The air that we breathe is typically 78 or so percent nitrogen, about 22% or so oxygen, and then about a 1% or so of mixture of some hydrocarbons, carbon dioxide, maybe some water vapor. So there's a very small percent that is not nitrogen or oxygen. That's true of the air that I'm breathing right now. That's true of the air that you're breathing right now. The air of the atmosphere tends to have a very fixed chemical composition throughout. And therefore, we will consider air, for our purposes, a pure substance. Now, it's important that we understand a few things about that. That can be in multiple phases. Right? So I could have water trapped in a vessel, some kind of a rigid tank. A rigid tank, again, is a closed system where the volume is going to be constant. So I could have, and we'll see this a lot of times with water or some kind of refrigerant like R134 is what we'll deal with. We could have some substance that's in both the liquid and the vapor phase. It might even have some solid components. Sorry, I don't know why I'm yawning there. I don't think we're gonna see. I don't know why this graphic is there. This is out of your book. I don't think we're gonna see air in the liquid phase, and we're not gonna deal with air if we get the temperature that low to where the nitrogen or the oxygen liquefies. But definitely could see it with water, some other substances. The whole point here is that we might be dealing with substances that are in multiple phases, and that's okay. We also need to acknowledge that it's not uncommon we're going to be dealing with a pure substance that is going to have some impurities. Pure water, right? If I have really purified water, it is going to be reactive and it is going to dissolve whatever it can find. Pure water wants to dissolve something. But here's the thing, once it dissolves a small amount, a tiny amount, it typically becomes inert. It normally quits dissolving things. The point there is you're not going to have just pure H2O. It's going to contain something. You put that pure H2O in a plastic container, it's going to dissolve some of the plastic into that H2O. It's not going to be 100% water. However, the impurities, the minerals, the salts, whatever it happens to grab onto and leach into it, as long as, right, if the concentrations are low, we will neglect them. And that's common. Right, so here's basically what I'm saying there is, if the text tells you that you've got water in the, if it just says you've got water or you've got air or you've got some other substance, then if they want you to assume that it's not pure water, if it's like seawater, for example, the text will tell you when you're dealing with seawater where it has dissolved a significant amount of salt and that has actually changed the properties of that water. It's not the same as pure water. If they want you to assume it's anything other than pure water, they will tell you, and they will give you enough information you can find the properties, or they'll give you the properties you need. If they just say you have water it's okay to acknowledge that it's not 100% water, but understand that it's, if they want you to assume it's anything other than pure water, they'll give you the information you need to treat it differently. Okay. Now, as I mentioned, you're going to have multiple phases. We're going to need to be able to deal with different phases, and so that means we need to have some understanding of what these phases are. Now, hopefully you've had a chemistry course of some kind. You've talked about the phases of matter, so we can go through this very quickly. Matter is going to exist in different phases, and there's three phases. We'll focus on solids, liquids, and vapors or gases. We're not going to make a huge technical distinction between vapors and gases. We can somewhat consider those the same, but let's start with solids. What is a solid? Well, a solid is when the substance forms what we call a crystal lattice structure, meaning the molecules fall into an orderly fashion. The molecules of the atoms will maintain an equal spacing and equal configuration, or constant configuration and equal spacing between each other. One of the best descriptions I've heard is think about molecules or atoms in a solid structure like they're attached to each other with springs. That's how this one's drawn here. So it's drawn these atoms attached to each other in springs, and that means that you can stretch them or you can compress them, right? And that's true of a solid structure. I've got solid metal here on this pen, and I can stretch those atoms. So see, I can pull those just a little bit. I can cause stretch, and then they go right back, just like springs do. You can heat it up and change those spacings, but this is a solid structure. Anything that forms a crystal lattice structure, these molecules are not going to move relative to one another, as opposed to a liquid. If the molecules are in a liquid phase, that means you can slosh those around, you can move those around, you can cause them to move relative to one another. They're still kind of trapped together. They're going to form this goo, this liquid. They're going to form a surface. They're going to separate from other gases, right? And some liquids will dissolve into each other, some will not. So you might have different liquids that separate from each other. But if you get to the liquid phase, that means the molecules are still in contact with one another. They still group together, they still clump together, but they're not fixed. They can move around relative to one another. So it's a higher energy level because now the molecules can move around. If you get molecules at a very high energy state where they can move around chaotically, they don't have to clump together, they're going to separate from one another. This is what we call the gaseous or the vapor phase. The movement of these molecules is going to be random, unpredictable. To get back to the liquid phase, we're going to have to release a large amount of energy. Okay, now fair warning, there's going to be a lot of just PowerPoint here for the next couple of videos. Sorry, it is what it is. But I'm going to try to keep moving along. Hopefully this is a review. Hopefully you've seen this part in a physics class. In a chemistry class. So again, graphically, you can see solid molecules fixed. They don't move relative to one another. If you add energy and get it to the liquid phase, that means that there's enough energy that the molecules can overcome the forces that force them into a solid structure, and they can move relative to one another. If you continue to add energy, you get them to the gaseous phase, and that's where the molecules can now separate from one another. They don't have to clump together, and they can move very chaotically and very erratically. Very high energy state. So increasing, right? You're increasing energy as you move this direction. And that's a nice place to stop. So we'll pick up the next video. Loud pop here.